While Fred's crew assembles the material for the airship's outer skin, the team tackles the next engineering challenge. The tether that anchors the turbine to the ground.
The tether is the most important component of this system. Not only does it need to be strong and lightweight, it needs to conduct electricity, and it seems to be one of the biggest engineering challenges we're facing right now.
The design demands on the tether are extreme. It's got to be light enough to let the airship rise to the target altitude, conductive enough to transfer electricity to the ground, and strong enough to handle at least 5 tons of pressure and weight without stretching or breaking. That 5-ton load requirement equals the weight of 5 mid-sized cars. And that inspires Jennifer to create an innovative experiment to test materials for the tether.
All right, bring it in.
They'll test 2 competing tethers by using them to lift a string of cars, each car weighing a ton. The stress should replicate 5 tons of drag acting against the turbine.
So what we're here to do today is basically check both the strength and the conductivity of our tether. In order to get the load that we need, I know we need to lift 5 cars.
Jennifer will test a high-quality steel cable first. Next, she'll test a tether made with a futuristic material called Vectran, one of the toughest plastics on the planet. To create it, the team has brought in microfiber engineer Jeremy Lawson.
Vectran has a great strength-to-weight ratio. Other materials that are as strong, like steel or other metal alloys, just weigh way too much. We had to use a fiber, and Vectran was the best option.
The molecular chains of conventional plastics are random and tend to stretch. Vectran molecules form in highly ordered chains, giving the plastic exceptional strength and stability. Over 500 Vectran strands will be woven together to form the core of the tether.
It's super lightweight, it's super strong, and to transmit the power, you really need something that doesn't have a lot of elongation.
Since Vectran can't conduct electricity from the turbine to the ground, copper wire must be wrapped around the tether to do the job instead. A revolutionary but untested design.
We've never tested the entire system in conjunction with the copper wire. It's very much a prototype.
The cars for the comparison test will hang first from a 15-foot section of steel cable, then from a 15-foot length of Vectran tether. The car headlights will be lit by an electrical current passing through the tether. If the lights stay on during the test, it proves the tethers could transmit wind-generated electricity from the ultimate aerial turbines. The winner will be the tether that can carry the most weight with the headlights still running. By nightfall, the team is ready to test the tether made of steel. A voltmeter will record any decrease in current as the electricity flows through the tether. A stress gauge will measure the weight as the cars, linked together by chains, are lifted one by one.
I've got 12 volts going in. We're checked and ready here. You're good to go, so you can go ahead and start the lift.
To pass the test, the tether has to suspend all 5 cars with their headlights on.
All right, I'm starting to get 200 pounds.
Stable on the electricity.
All right, the second one's off because we're at 4,200 pounds. We're at 6,370, 6,370 pounds. So we are just over 3 tons. The sheathing's broken.
The orange skin of the tether is coming apart, a sign the steel cable is stretching.
It's getting longer, it's gonna go. There it goes.
I guess that's what you call a compact car.
The steel tether broke at 3 tons. That's 2 tons under the target goal. That means if the steel tether was holding the airship, it would break under the strain of a mere 20-mile-an-hour wind. Everything's now riding on the copper-wrapped Vectran tether. Jennifer is still worried this high-tech, untested plastic cable will break under the strain of a 5-ton load.
So this is your design, Jeremy.
This is it, the real deal.
Are you ready to start this?
Let's do
Ready
it.
to see it.
Okay, let's start the lift. What we're looking for is 9,400 pounds. We're at 2,200 right now. We need to see 5 cars off the ground. 4,100. 4,100 pounds on the tether. Getting ready to go for 4 cars. We're at 6,400 pounds now.
The steel tether snapped at this weight.
We're at 8,400. So we are 1,000 away. 1,000 away from what you need to make your experiment work.
We're almost there.
We're at,
5 cars.
let's watch it there and make sure it holds.
The Vectran tether is holding all 5 cars with lights on. That's when Jen ups the ante.
Let's lift that last car. So the tether has 12,000 pounds. 12.4, 12.5, 12.6,
It's off the
12.8.
ground. It's off the ground.
12.8, and it's off the ground.
There you go.
6 cars.
Check the volts.
The headlights are still on.
The volts are holding. All the headlights are lit.
Good stuff.
All right, Jeremy.
There.
Awesome job.
That's great.
Well
guys.
done.
Thank you very much.
Absolutely well
That's a
done.
lot of work. That's great.
The Vectran tether has surpassed all expectations. 9/10 of an inch in diameter can hold an astounding 6 tons of dead weight.
I'm extremely impressed with the Vectran. I never thought the thin strands of hair would actually hold up 6 cars. I think this is going to work.